So we're going to talk about logs today, and the reason we talk about logs is because we have studied exponential functions, a number to an x power that equals another number, right? We've studied those, 2 to the x, 3 to the x, and so on, and graphed them, looked at transformations. The reason now we're going to be looking at logs is because, like I've said before many times, the only way to solve each of these is with its inverse. These are inverses of each other, okay? So the only way to solve an exponential function is to use the logarithmic function. The only way to solve a logarithmic function is to use the exponential functions. So we need to look at this property. This is the most important property that we'll have out of all those log properties above my board. It's the very first one, and it's the most important because you cannot continue in this chapter without knowing this property. So if you look at this, it's coded for you. The base of the exponent is the base of the log. It's a subscript. It's a small number. The answer of the exponent is what the log is a base of. And then the exponent is then what the log equals. So we'll be using this property, and we're going to practice how to put exponential into log, log into exponential form. We're just going to practice that.
What's log mean?
So look at the first example here.
Okay, got you.
I have 8 squared equals 64. Okay? 8 acts like my b, the 2 acts like the x, and the 64 acts like the a. So if I wanted to put this in logarithmic form, I would have log of base b, which b we know is the 8, so I write a small 8, it's a subscript, of a, which is the answer, 64, and that's going to equal the exponent 2. That is the inverse function of that exponential function, and that's how you write it.
What's the point?
Exponential function, I have 1/2 to the -2 power equals 4. So how would I write that exponential in logarithmic form? Log of base 1/2, because 1/2 is the base of the exponent, of 4 equals -2. There's the log form. Look at the next example. Log of base 1/3, because 1/3 is the base of the exponent, of 127 equals 3. That would be the log, the inverse function. Here's another one. We'd say log of base 10 of 1/100th equals -2. Right? And the reason I wrote that smaller is because I want to show you something. When you have logs of base 10, another way you can write this is like this. This is how you will see it from now on. We don't write the base 10 because logs of base 10 are the most commonly used logarithm. So we call this the common log. So whenever you see a log function without a base, it's 10. We assume it's 10. Going the other way, if I give you the log function, can you write it in the exponential form? Okay. So what is the base of the log? 2. So the base of my exponent is 2. The answer of the log is the exponent, right? And what the log is a base of is my answer. And when you do it this way, you can actually check mental math. 2 to the 7th power is 128. It should be true. The other way to do this, which is easier, this is how I always visualize it in my head, I do a circle. I do 2 to the 7th power equals 128. Okay. So like this one, what's the base for this log? There is no base, so it's 10. So I can say 10 to the -4 equals 1/10,000ths, right? This one, I can say, what, 6 to the 1st power is 6. This one I can say 4 to the 0 power is 1. Right? And those should be true. Evaluate the logs. What we're doing is we're trying to find what this equals to. Log base of 2, 8, equals what number? Okay? So we convert this into an exponential form. We can say 2 to the x power equals 8. Right? Now, with some mental math, 2 to what power is 8? 3. So we know that this log equals 3. Your answer is 3. Okay. So like this one, we don't know what this equals. Log base 49 of 7 equals what? We don't know. So we write it in exponential form. 49 to what power equals 7? We got to recall last chapter. 49 to what power is 7?
Square root it.
We know the square root of 49 is 7. So the power that represents square root is 1/2. Very good. So this would be 1/2.
Oh my god.
49 to the 1/2 power is 7. Okay. Let's do the one below it here. So we don't know what this equals, right? So we say 2 to what power equals 2 to the 5th power? 5. Great. 5. If I have 2 to the 5th power, the only other thing this can be is 5. You can't have 2 to the 5th power equals 2 to the 7th power. That's not true. 2 to the 5th power can only equal 2 to the 5th power. Okay, so this is 5. Okay. How about this one? 1/2 to what power equals 1/2? 1. Great. The only way to get itself is with a 1. Anything to the first power is itself. Okay. All right, how about this one? 5 to what power equals -25? 5 to what power would give me a -25? Not possible. We say no solution. You cannot take a positive number to an exponent and get a negative number. That's not possible because if you remember from last chapter, if I have a negative exponent, that equals this, 1/5 squared. I make it positive. Okay? If you had a negative number to a power can be a negative number. But if you have a positive number, there is no power that can make that negative. Impossible. Undefined. Okay. How about this one? 3 to what power is 9? 2, right? You guys can do that in your head yet? 5 to what power is 125? 3. Good. So what base is here? 10. 10 to what power is 10,000? You have to think scientific notation. 10 to what power is 10,000? I have 4 zeros, so 10 to the 4th power. Remember that? 10 to whatever power, how many zeros you have? 10 to the 4th power is 10,000. Right? If some of these you don't know, use your calculator, do a little bit of guess and check. It'll help you out. Okay. So I do want to include some graphing of these logs and exponential because they're inverses of each other, and I want you to see, visualize that inverse function. Okay, so these are actually inverses of each other. These two problems go together. Log base 2 is an inverse of 2 to the x power, right? These are inverses of each other. Okay, which one can I graph on a graphing calculator? 2 to the x power. Remember, I told you your calculator only does log of base 10? You can't plug that into your y equals. But on Monday, we looked at, how to graph exponential functions. We went to our y equals, we put in 2 to the x power, graphed, and used the table to find points. Okay? So if you put 2 to the x power into your graphing calculator, you can get a set of points to graph that. Right? If you look at your graphing calculator, you should get right? Those points. And there's my exponential function. We can see it's an exponential growth. We already studied that. Okay. Now, how do I graph the inverse function? If I can't put this into my graphing calculator, but I have this function, how would I graph an inverse function? You flip the x's and y's. Very good. We studied last week with inverse functions is that any function, to graph its inverse, all I have to do is switch the x's and y's. So to graph this log, all I'd have to do is switch my points around, and I will have the logarithmic function. Right? And I can graph those. And what I want you to notice when we studied inverse functions, if I sketch that y equals x line, remember that? This should be an inverse over that line. And you can see that. So you can see that this blue reflected over that line and we get the inverse function. So again, these two are inverses of each other. If I have a base 1/2 to the x power, the inverse of that is going to be log of base 1/2. Okay. So again, this is the one I can put in my graphing calculator to find points, or you can use some mental math. Anything to do with 0 power is 1. Right? Find some points to graph, and I can graph those. And you should see it's an exponential decay because 1/2 is less than 1. And then again, to do the inverse function, I'm going to take those points and flip them. And again, you should see if I put in that y equals x line, that blue function reflected over that line, and that's how I got the red function. So just like exponential functions, we can take logarithmic functions, move them left and right, up and down, stretch and compress. So if I start with a log of x, right, and we'll say any base, doesn't matter, okay, any base, so any number can be there. When I'm adding, subtracting to the whole log, that is going to be my up or down. When I'm adding, subtracting just to the x, and that is going to be indicated by parentheses, that is going to be my left or right. Okay, so parentheses are really important on the log. Parentheses is adding left and right. Outside parentheses is up and down. Of course, if I multiply by a number, that's a vertical stretch or compression. So if I multiply log out here, this would be a vertical stretch if it's bigger than 1, compression if it's less than 1. And then, of course, if I have negatives, negatives always mean reflection. So if I have a negative here, that's going to be reflect over the y-axis, no, x-axis. If I have a reflection here, there's a negative, that's reflect over the y-axis. That's kind of the blueprint I can give you of all your transformations. So looking at a log, can you describe the transformation? So if I see log base 7 of x minus 2 in parentheses, what transformations occurred? Right 2, very good, because it's in the parentheses. What about this log of base 4? What transformations happened? Very good. Left 2, because I'm adding 2 in parentheses. This would be down 1, because I'm subtracting outside the parentheses. So this log of base 5 would be what? Up 1 because there are no parentheses.
Good.
Okay, what about this log of base 3?
Down.
Right, 5 and
Up 3.
up 3. Very good.